Yeah. So.
First, I must confess that I'm not an algebraic geometer, so if I would switch into using some differential geometric language or whatever, please excuse me. And let me start with the following. So perhaps all of you know the Schottky problem, which asks for a way to characterize Jacobians amongst all principally polarized abelian varieties of given dimension. Since I'm not an algebraic geometer, I would formulate it in a slightly more weird way, just for a reminder. So I'll formulate it like this. So let S be a genus G surface, just topological, and V throughout all the stuff would just mean the topological H1 of S with complex solutions. So it's a complex vector space with its intersection form and the integral structure. So the Schottky problem in this language I would formulate this way: for which subspaces of dimension G in this 2G dimensional space there exists a complex structure on S, which makes it a theorem surface or a complex curve, such that U equals H10 of this Rodion surface. So, which subspaces can be realized by holomorphic conforms or algebraic conforms? And those of you who heard this problem know that there is a necessary condition which I already formulated by saying that it should be an abelian variety. So the necessary conditions are the so-called Prym relations, which say that for any alpha and beta in such a U, or I think just say this omega restricted to U is identical to 0, whereby omega is the intersection form, so omega alpha and beta is integral of alpha dash beta over S. And the Hermitian form omega of XX bar restricted to U is positive definite. If the dimension is greater than 3, then of course it is not enough, and there is no brief answer. But for a and one can ask a simple problem, namely the one which is referenced in the title. Which is very similar to the Schottky problem in this exact formulation, namely for which alpha exists a complex structure on S such that alpha belongs to H10. So instead of asking for representation of an entire d-dimensional subspace, we ask to represent just one particular class, or to describe the union of all these possible subspaces. And here there is a complete answer, which was given twice, as the name of the theorem suggests, first by Haupt-Kapovich in 1920, and then by Haupt-Kapovich, who was not aware of Haupt because Haupt was writing in German, in the year of 2000. And the answer is as follows. Let lambda with this subscript alpha denotes the set of all the integrals of alpha over the classes in first homology class. So the set of the periods of a given of a given form. So then the class can be realized. I mean, first, of course, it should be subject to this relation. This is already necessary. And then either this is a subset in complex numbers, a subgroup. Then either it's dense or this is a lattice, and the covolume or co-area of area of C mod lambda alpha is strictly smaller than omega of alpha bar, and I should write -1 here because yeah. So the only possibility in which it cannot be realized, provided this is positive, is when this inequality turns into equality. And it's actually quite clear when this restriction comes from, because if you have a suppose we have a class of holomorphic one form which has this property, then integration of this class along like path integration yields you a map from your curve to an elliptic curve, C mod lambda, and oh yeah, of course, G is greater than 1. Yeah, and if it's a holomorphic map from a genus, a curve of a genus S to an elliptic curve, it cannot be an isomorphic. So this is at least twice as much as this covolume of this lattice. Surprisingly, this is the only condition. Whereas the answer for the Schottky problem is like there is no perfect answer. And but again, if you look on this, then one may ask, why should we also only care about one class or about all G classes simultaneously? So what I was dealing with is the interpolation between these two problems, which I call Kapovich problem.
Can I ask you, what is the constant there in the bond for the area?
Well, it's square root of -1. So I just normalize it so it would be real positive. Yeah. Yeah. So the problem is like let K be between 1 and 2. k-dimensional subspaces in V. There is a complex structure I on S, such that U lies inside H10 of S I. And the answer is there is a dichotomy. So for k equals 2 or 3, there exists an open dense subset in the Grassmannian of all isotropic positive definite subspaces, which I denote by Bruce plus KV, which can be realized. Whereas for k greater or equal to 4, the generic subspace subject to quadrivial relations, of course, cannot be realized. Which is again similar to the situation with the Jacobian varieties, because generic abelian variety of dimension 2 or 3 is a Jacobian principally polarized abelian variety of dimension 2 or 3, whereas starting from dimension 4, it's not. It's all true. Let me immediately tell you the strategy of this group. We want to describe the union. We can first think of k equals 1, because I suppose not everyone is familiar with this proof, and then we will maybe give a brief description of what happens for k equal 2 and 3. So we want to take the union of all H10 for all possible complex structures. So in order to do this, of course, we could have worked on over the modular space, but since we want to make it into projections, we take the universal cover. So we pass to the Stake-Muller space of S. And over the Stake-Muller space, we have for the trivial bundle of the first cohomology, which projects whose total space projects into V. And within this bundle, whose fiber at each point is H1 as the complex coefficients, we have the subspace H10 of Si. So this becomes a variation of with one-touch structures. And so from this total space of this H10 bundle, we have a projection to this V. So this is and here the union of all H10 subspaces becomes a certain code. Yeah, and first we have two steps. Step one is this projection map is open, and to consider k-dimensional subspace, here I just consider the fiber was Grassmannian bundle, and here the open subset of the isotropic Grassmannian. So and this I would denote by P within index k, and P, which is equals P1, is open, and Pk for k equals 2 and 3 is open and generic point. Not even open, but it's dp is surjective, and dp 2 and 3 is surjective at generic point. So and here the algebraic geometry starts playing a role, because morally you can think of the following: a pair of one forms is like an extremal pair of one forms is the same as a map from the curve to an abelian surface, and the failure of surjectivity indicates the singularity of this embedding. Yeah, and yeah, so this is the first thing. So here we know that it contains some, the image contains some open subset. How do we conclude from here that almost everything can be realized? It can be done by step 2. We pass to the Teichmuller space, to the universal cover. So there is an action of the mapping class group of S, which on the first cohomology, of course, factorizes through the integral symplectic group, which acts here, and then we use homogeneous dynamics for the group SE to GZ. And for example, we conclude that if there is an open orbit of this, an orbit of the section which contains an open subset, then it should be open dense. Its complement being of measure 0. Moreover, contained in a certain union of closed orbits. But since this is more, the first step is more algebraic geometric, let me start with it. Yeah, so in the context of the Riemann surface, this is for some reason called the Haupt-Kapovich holomorphic theorem, at least by Kapovich, but I don't know much about this geometric part of this, yet I retain the name for the lack of better one. But put it. Which holonomy of what is this? I don't know. So this is what was called what they call above the step 1. So we want to understand the differential of this map, which goes from the I write for any k, so tau is a k-dimensional subspace. And then it goes to the tangent space, the isotropic Grassmannian, which is, by the way, isomorphic to tangent space for any Grassmannian is isomorphic to from tau to v mod tau, but here, since we want the space to stay isotropic, we put here 0, which indicates that this map is balanced. So alpha belongs, or F belongs to from tau to v mod tau if with this no superscript if for any xy in tau one has omega of fx y equals omega of x fy. This ensures that the subspace stays isotropic. And last denotes an open condition, so that doesn't affect the tangent space. And yeah, so this is a tangent space to a total space of another actually vector bundle. So we have a vertical component, and this P also has a vertical component. But on the vertical component, it's trivial because H10 embeds into H1. Feel free to interrupt me if I'm going to solve or going to fight or whatever. Yeah, so yeah, and this is of course isomorphic to from tau to H10 mod tau via textbook isomorphism, because H10 embeds here, then tau aligns in H10. So
I have a question.
Yes.
For your omega is defined on.
Omega is an in intersection form, which I consider as an integral symplectic form on the space V.
Okay, so for your map F, it sends an element in tau to the modular of tau. So how do you make the omega m for x, y?
I mean, tau is isotropic, so omega becomes a pairing between tau and V mod tau.
Okay.
Yeah, sorry, I did not make it clear. And so the only interesting new thing which can be realized would be realized by going around the tabular space and tilting H10, of course. So we have a map from the tangent space at I to the tabular space, which goes to from tau to H0. So if we want to prove surjectivity, we first need to understand what is this arrow, and secondly, when it is surjective, because the first component is an isomorphism. And I'm not going to prove this because it's like a very classical deformation theory for curves. So this first, I should remind that this is isomorphic. Oh, of course, it's isomorphic to H0 or H1 of the tangent bundle of. I would try to somehow compromise between algebraic and differential geometric notation. Yeah, which is isomorphic to the dual of the space of quadratic differentials. And it goes to from so it's tau star tensor H0 K this one dual, and it lands into this balanced part of it, and yeah. So the claim is that this map is given by a very simple formula, psi times alpha goes to psi of alpha times something. Here psi is a function on quadratic differentials, and I perhaps should better write throw those stuff from here and stop. Yeah, so I mean, out of a linear function on quadratic differentials and a one form, one can make only one function on one form. And from here we deduce the second part of the case k equals 1. The map from H0 k times some one class alpha 1 to H0 k and is always surjective. This essentially asks when multiplication of two algebraic one forms is 0. I mean, the symmetric multiplication. It can only happen when one of the forms is itself 0. So the second is this map from to H0. Here everything is projected. If and only if alpha and beta may have common zeros, but not too much, namely H1 of the following divisor, where the alpha and beta is the divisor of common zeros. And there's multiplicity, of course. This is projected if and only if this equals 1. Or actually, what can be said is that the here stands not. We could not write it not, and if no, then the co-kernel of this map would be isomorphic to the dual of this H1. So this is already an algebraic condition. And then number 3, for 3 classes, the map notice that this is g-dimensional, this is 3-dimensional, so this is 3G dimensional, but the not condition implies that it is of dimension 3 in this tensor product. So if it is rejected, that it is an isomorphism. Is an isomorphism. If and only if all the quadratic differentials can be represented as monomials which include alpha, beta, and gamma. The entire space of quadratic differential is spanned by monomials of the following form: alpha times something plus beta times something plus gamma times something. And there is this Noether's theorem on the quadratic differentials, which tells that for a non-hyperelliptic curve, the space of quadratic differentials is actually spanned by products of one forms. But there is a refinement of the theorem which tells that actually for any non-hyperelliptic curve one can find three one forms that are products with which span the entire space of quadratic differentials. And a generic triple would actually work. Maybe I will prove it for some genus if I have any time. Yeah, so let me tell an example for G equals 4. So of what is happening? A non-hyperelliptic genus 4 curve embeds canonically into P3, and it is of degree 6. It is an intersection of a quadric and a cubic. So for this condition, for a pair. So let me first draw a picture. Like we have some curve, which so this would be our canonical curve, and it's a quadric on which it lies, and it's it has by degree 3. First, a pair of one forms, like one form in the canonical embedding is a hyperplane section. So a pair of one forms is a section by something, or maybe not a section, just a linear subspace of dimension 2. In this case, it's a line in P3. And what is like the most special line we can get here? It would be a line on this quadric. So it will be a 3/2 of the canonical curve. And yeah, so this condition actually tells that H1 of d tau is it can equal either 1 or 2, and it equals 2 if and only if tau is 3/2 or aligned on like this P3. And yeah, so this is these 3 points are exactly this delta tau. And if I yeah, so in this case, the existence of more than one section is equivalent to yeah. There is an application of Riemann rock find hidden somewhere, but let me just tell what happens here. So actually, let me prove that for in this in this case we may find a triple of one forms which spans the space of quadratic differentials. So promote it as proposition 3. Let the degree of d tau be 2. So we have just not 3 seconds, but just some seconds. Some form of this canonical curve. And gamma is one form with no zeros in delta form. Then and tau is also scanned by alpha and beta. Then these tensor problems with alpha, beta, and gamma span the entire space of quadratic differentials. Let me alpha be the space of all the quadratic differentials which are divisible by alpha and L beta and L gamma respectively. So we have 3 subspaces, and we want to prove that. First, maybe let me explain what this happens. So here we want to say that this map is projected, so that any linear function from a pair of differentials to the functions on H0 of k can be realized by contracting them with some quadratic differential. Essentially, this means the following. So we look at 2 subspaces, L alpha and L beta, which are both isomorphic to H0 of k, of course. Yeah, so, and we have a pair of linear functions here and here. When can we realize them by a restriction of some linear function on the space of all quadratic differentials? If and of course, if and only if they intersect by something one-dimensional, because they always intersect in the quadratic differential alpha times beta, and the fact that 2 maps agree on this intersection corresponds exactly to having not here that this map would be balanced in this sense. And if we have a larger intersection, then we have an abstraction to subjectivity. And what is alpha intersect with L beta? It's a space of all quadratic differentials which have the same zeros. Like we can have a, if we have some quadratic differential psi here, we can divide psi by alpha times beta. The only poles which this thing can have occur in the divisor of common zeros of alpha and beta. So this is a meromorphic function yeah, so meromorphic function belongs to the maybe should I put 0 here? But I need to consult my note, but I don't know where they are. So you get the idea. So yeah, and here for three subspaces L alpha and L beta and L gamma to span the entire H0 KC squared, we need so that they would agree on three pairwise intersections, and that is mapped from L alpha plus L beta plus L gamma to the space of quadratic differentials would have on the kernel of dimension 3. And this kernel is it can be identified with H1 of the. Here it would be something else. Actually, it's quite easy to write it down. So we consider a triple of alpha, beta, and gamma as mapped from the tangent sheaf to O plus O, and take the quotient. So it's something like a normal bundle, and if alpha, beta, and gamma were algebraic one forms restricted from embedding to some abelian threefold, then it would be exactly the normal bundle of the embedding of this curve into a threefold. And here, this is something more general. Yeah, so let me finish with proving this. Suppose there is some kernel of this map, so that the span of L alpha and L beta has some intersection with L gamma. Suppose we have some class here. I won't even go into use any letter for that. So gamma times something equals alpha times something plus beta times something. So this side has zeros in delta term, and therefore this side also has. But gamma has no zeros in delta term, so it implies that it also has zeros there. And we know from this condition, or for the line not being 3-second, that it forces this omega to be a linear combination of alpha and beta, and therefore everything turns out to be spanned by gamma times alpha and gamma times beta. So. And this argument actually generalizes to any non-hyperelliptic curves. You just cannot draw a picture. Since I don't have much time left, let me notice just one thing, that this picture, when presented this way, can be generalized to many things which are not curves, because we can actually take any variation of polarized weight 1 Hodge structures, lift it to the universal cover of the base, and consider the union of the fibers under the projection, which is given by flat connection. One may ask the same question about whether the limit of this projection is projected. And for example, in the case when where you have a hyperelliptic manifold with a Lagrangian vibration, the corresponding H10 on the base outside of the discriminant locus also has this property. I think it has been proved by Voisin and Van de Gemmen, but I'm not sure if it's stated explicitly. So this phenomenon is not something special for curves. And for the case of the moduli space of hyperelliptic curves, we have very theorems very similar to these. So for one class it is the derivative is surjective, and for two classes, the derivative is a bijection generic point. For all the curves, it will be for three classes, and for hyperelliptic curves, it happens for two classes. And
you never use that k can go up to g minus 1.
yeah, because of the second statement, which is it's very easy. It's just computation of dimensions. So a generic four-dimensional subspace can never be realized.
Yeah, but my point is that
Yeah.
is g.
Yeah. So here I can use k equals 2 or 3 actually, because k equals 4 or greater. I mean, it would be something. It would not be. The image would not be open. So yeah, and I am only all of my talk is devoted to the case when where the image is open. And for example, I don't know how to characterize it for k equals 4, except for the case when g equals 4, in which I think was characterized by Schott himself. Yeah. So. Yeah, let me just briefly mention what let me just sketch what is going to finish the proof. So let me state again without the proof of a classical theorem of Calvin-Moore. Let G be a semi-simple Lie group. H inside G non-compact. And gamma inside G elliptic. That is a discrete subgroup of finite covalent with respect to power measure. Then gamma acts on G mod H ergodically. Meaning measure preserving and with the invariant subsets either of full measure or of measure 0. And let me notice that this let be a proposition that the Grossmanian of isotropic subspace is of positive isotropic subspaces is a homogeneous group for a real symplectic group. It is a homogeneous space for the real symplectic group with the stabilizer sp to g minus 2k r times uk. Yeah, because if we have an isotropic subspace, we can take it in its complex conjugate. They span a real 2k dimensional symplectic subspace plus a complex structure on it. So the stabilizer of this thing is this subgroup. And whenever k is less than g, this theorem is applicable. And we have an open, an invariant subset which contains an open neighborhood of some point, and therefore it's of full measure, because it is invariant under SP to GZ. And this argument also generalizes to other variations of Hodge structures if we know that, something about the image of the monodromy. For example, in the case of hyperelliptic curves, the monodromy of the hyperelliptic curves on cohomology is, I think, congruence to subgroup in SP to GZ. So the various same argument implies that a generic class can be realized, but then we need to clarify what does it mean for a class to be generic. Yeah, I still have 5 minutes, so let me formulate. It's one of my favorite theorems, so it's a theorem of Ratner, which says the following. So suppose G is a reductive algebraic group, and U is inside it a subgroup generated by unipotent elements. For example, upper and lower triangular matrices generate this subgroup. Essentially. Yeah, so X would be now G mod U, and again gamma in GLS. Then for any X in X, the closure of the orbit of X is an orbit of some group H, which lies between U and G. Some H, and this H has the following property, that H intersect with gamma is a lattice inside H. Yeah, so then for an it's a bit tricky moment, but for k equals 1, we can, but actually for any k, we can consider the map to SP to G minus 2k times SP to k. But for k equals 1, the locus of realizable classes would be a pre-image of some locus here. It happens because there is a thing called SL2R actions on action on abelian differentials, which is ubiquitous in Taylor dynamics. And this does not generalize for even for k equals 2. And yeah, so when applied to this homogeneous space, we know that this subgroup is maximal here. So this H could be either the whole group, which implies that the class is generic, so its orbit, the closure, its orbit is dense, or it is a product of two subgroups. And then if here k equals 1, so if G is not equal to 2, then this is product of two groups with non-isomorphic complexifications of their Lie algebras, and therefore any lattice here splits into a pair of lattices here and here, and sp2 with its lattice, it corresponds to a class with just two independent periods. So class is coming from mapping to toric. But an interesting, an interesting thing here is that when G equals 2, then there are lattices in SP SL to R times SL to R which do not come from a pair of lattices. Namely, if you consider a real quadratic field, then SL of its ring of integers can be embedded into SL to R times SL to R via the two embeddings of the field. And there are curves, pairs of a genus 2 curve plus a class which correspond to these sublattices, and these are exactly the genus 2 curves whose Jacobins admit real multiplication by an order in this ring of integers of this field. So this is the last thing I wanted to mention. I have something else, but I have no time, so thank you.